Hello, today I'd like to talk about voltage control. We copied the PQ formulation of the two-node system in the first video here and set G equals to 0. We can see that active power flow is driven by voltage angle difference, and reactive power flow is driven by voltage amplitude difference. Note, I'm just talking about this coupling relationship for steady states. So we hope voltage amplitude to be near 1 per unit everywhere in the system. Voltage amplitude difference between two nodes cannot be too big, so reactive power control should be done locally, which is often mentioned as power factor correction. We can also look at the voltage drop between two nodes in the phasor form. So the real part of voltage drop is driven by Q, and the imaginary part is driven by P. In power systems, there are motors and transformers which are inductive because of magnetization. And there are series elements from transformers, cables, and lines which bring reactive losses. All of these components require reactive power supply. Meanwhile, shunt elements such as line and cable capacitance can provide reactive gains. If we hope more reactive power supply, choices are as follows. Let's talk about them one by one. First, synchronous machine. The basic idea for synchronous machines is that changing mechanical torque can adjust power angle, and changing field current can change excitation voltage amplitude. They can be controlled separately. Now let's talk about the limitations on synchronous generator operation. On the PQ plane, first there is a lower and upper bound of active power generation, that is prime mover mechanical power limit. Then there are thermal limits on stator windings, which is related to the stator current Is max. If we assume the terminal voltage to be 1 per unit, then Is max is equal to the apparent power S max. This corresponds to a circle in the PQ plane. The third limitation is from excitation current IF. If IF is too small, that is under excitation, then the coupling is not strong and would affect transient stability. If IF is too large, which means overexcitation, then there's problems with rotor windings or stator insulation. And this corresponds to two circles in the PQ plane. Synchronous condensers are also synchronous machines, but they only provide QV control. They can also serve as source of inertia for frequency control. To perform QV control, capacitors and inductors are shunt connected so that delta V can be large. We can't expect a Q set point because it is related to voltage square. Depending on high or low load situations, we need either capacitors to generate Q and rise voltage or inductors to absorb Q and reduce voltage. There's also series compensation, but it's used to boost transient stability performance by directly lowering X, or to reduce short circuit currents, and it is harder to install them. A static Vol compensation is formed by several shunt-connected capacitors plus a thyristor control inductor. The inductor is to provide continuous tuning. The difference between all these above devices and static compensators is that Q output in StatCom is not voltage sensitive. Switching circuits can also serve as QV control. Regulating transformers typically combine tap changing and phase shifting, thus it can adjust voltage magnitude and power flow. Let's see how tap changers can serve as reactive power pumps. We want to get rid of this and get a Y matrix to simplify current voltage relationships, and finally draw a pi equivalent circuit and represent all admittance values with the adjustable turn ratio T. A phase shifter works like this. There are two same parallel lines and they share the active power flow. If we insert a phase shifter in this line to increase the voltage angle here, then the angle difference across this line is reduced and the reactive power transferred by this line is reduced. We can assume a voltage at this point and do the calculation. Thank you for watching, and in the next video I'll talk about frequency control.